तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Towards the end of the previous lecture, we considered the design of JK flip-flop, specifically master-slave JK flip-flop. We just started that. Why did we take up this particular design? Mainly because this particular design will involve a few states, a couple of inputs and a couple of outputs to deal with, and hence only a few states to deal with, and then the whole design can be explained both from the hardwired control point of view as well as from the micro programmed control point of view. Okay? Otherwise, if you just start discussing the CPU design, then there are too many states and too many issues, too many inputs and outputs to be considered. So, as an example we are considering this, bear this in mind. Good. In fact, we had worked out the table. That particular table is called truth table or excitation table, specifically with reference to flip-flop, with J and K as the inputs and the present state, what's the next state. And in any state we know a system develops an output, right? Good. But though we talk about states, bear this in mind that essentially in any system design we are concerned with the inputs to be handled and the outputs to be generated, nothing more. The state the system goes through, we may call the state as a necessary evil, that is what it is. Okay. So, state is only means to achieve precisely the ends we want. We are not really bothered about the state, but this digital system goes through states in accepting the inputs and in generating the outputs. So, really speaking, the input and the output, the relationship between this is what precisely we are interested in, and states come in between. Good. Now, we said in the previous lecture itself that the inputs we may call them as Yj, Yk and Yc, that is the J and K as the input and C is the clock input, because in any system if you have a clock, then we can synchronize the generation of the output with reference to that clock. That is why we have a clock, and that is one reason why a system having a clock will be called a synchronous system. Okay? It is also possible to have instead of a synchronous flip-flop, we can also have the other one called an asynchronous flip-flop. Okay? Now, system, though I say here what we are talking about is just this component flip-flop as this. Instead, one can also have an asynchronous one. In that, if you have that asynchronous system, the clock will be absent. What it means is, as soon as the inputs change, the output will change in asynchronous system. Okay? The asynchronous system, as soon as the inputs change, the output will change, and internally there may be state changes. All right? Whereas in the synchronous system, just because the inputs change, the output may not change. It will be synchronized with reference to the clock. Okay? And while discussing this flip-flop and its behavior, we had not considered the clock yesterday, remember? Now, let us go to the chart and take a review at that particular excitation table. Now, you must be familiar with this JK flip-flop, and specifically I am going to talk a little more for those who have not yet been initiated into switching theory and logic circuits. Okay, those who have done a course on switching theory and logic circuits, this may be a repetition. Well, good. See here, you can see this. These are pairs. Okay, 0 0. That's one pair. Then you have a 0 1 pair, then a 1 0 pair, and a 1 1 pair. Now, because we are considering these for the given present state, what is the next state? So, for in one the state may be 0, and we are considering the second case the state as 1. That is why we are having the pairs of inputs here. Okay? That is, for a given input j and k, let us say 0 and 0 as here. For the present state 0, what is the next state? And for the present state 1, what is the next state? That is what we are saying here. Good. Now, see here that as long as k is 1, that is in this particular pair 0 1, j is 0, as long as k is 1, we find that whatever may be the present state, the next state is 0. That is why I said k can be considered as a reset input, which means which causes the output to go 0. That is the next state to go 0. And similarly, look at this pair. J is 1 in both these. Now, whatever may be the present state, the next state is 1. So, we say J is equivalent to an input, set input. Now, what about this pair? In this, J and K both are 1, and we have already said that whenever you have j and k both are 1, it does not mean it sets as well as resets. Basically, it means it toggles. Whatever be the present state, it just goes to the other state. If it were 0, the next state will be 1. If the present state is 1, the next state will be 0. So, this in fact is a toggle input. Good. So, now you can see that if j is 0, okay, then when k is 1, the next state will be 0. If k is 0, when j is 1, the next state will be 1. And if both j and k are 1, then the next state will be complement of the present state. If it is 0, the next state will be 1. If it is 1, the next state will be 0. That is what it is. Now, one more thing you may notice here. See here the k input, okay. Take a look at this k input here, 1, okay. Few points. Okay, maybe I will explain this further as we proceed along, right. Now, in this excitation table, which actually gives the relationship between the present state and the next state for a given inputs, okay. For a given input, it basically gives the relationship between present state and next state. In other words, what we say is how this flip-flop gets excited, okay, by its inputs to assume the new next state. That is why it's called excitation table. Fine. But in our case, we not only have these two inputs j and k, but we also have the clock, right. We have not yet considered that. We have to consider this clock also. Now, if I include the clock in the particular excitation table, then the table will become unwieldy. So, I will just explain. There is a reason for that. What is that? There is, with the two inputs j and k and the present state. So, actually there are 3 variables considered. That is why we had in that particular chart, okay, take a look at the chart, there are 8 states, right, there are 8 states. That is because j and k and the present state, 3 variables are considered. So, 2 to the power 3, 8 you have. Now, if you include YC clock also, then it becomes 2 to the power 4, 16, right. So, the size of the table will become double, and it is not really necessary, okay, to take a look at it. And there is one other thing, we have only talked about the JK part, we have not yet talked about the master slave part. that particular thing is linked with the clock. Now what is that? It's like this. Whenever the clock changes, now clock we can just take as a sequence of inputs. You remember what we were talking about earlier? The clock is the one in the processor which will be defining the state, and so really speaking a clock is a state defining input, right? Whereas you can consider in this case J and K as possibly data inputs. The clock is in fact the state defining input. Okay, right. Now in a master slave flip flop, this is what's happening. In the racing edge, that is this particular one, in the racing edge of the clock, the inputs namely J and K will be sensed, and internally the flip flop will go through some state change. It will not immediately affect the output, and in the falling edge of that clock the output will be generated. In other words, on the racing edge, okay, or right here on the racing edge, inputs are sensed. Inputs are sensed here on the racing edge, and on the falling edge of the clock, okay, output generated. If more than one output, okay, outputs generated. This in fact is the principle of the master slave. Well, what is the idea behind this? It basically says whatever may be the state of input after this edge, it's not going to affect the output subsequently, the behavior of this flip flop subsequently. This is quite useful, especially in the case of some noisy situation where there may be some noise on the inputs J and K, okay, and by the time the clock the falling edge comes, the state of the input may have changed. It can affect the behavior of the system, okay. Good. We will not go too much into it. It's in fact the electrical engineering consideration I would put it. Okay, from computer science point of view, it is the logic we will take a look at, right. So the inputs are sensed during, let us say, the rising edge of the clock. What I mean is when clock, let us say YC becomes 1, that is, let us say if this were logic 0, this is the logic 1. So when clock becomes 1, what is input that is sensed? And when the clock falls back to 0, okay, the clock falls back to 0, that's the one level, this is the 0 level, okay, the two levels are here. That's the logic levels, we say, whatever may be the voltage or current levels that may be. Good. So the outputs will be generated during the falling edge, inputs are sensed during the rising edge. It can be the other way also, meaning for instance the input can be sensed during falling edge, the other one, it does not matter what it is. Then in which case we will be considering this as the clock duration, that is all, okay. Instead of this we will be considering the other one, hardly matters what it is. Good. Now you can see the master slave, what exactly is the principle? It says during the rising edge of the clock, sense the inputs and prepare the system's outputs. It only says prepare the system's outputs. It does not change the output immediately, and actually affect the change in the output during the falling edge. This is the master slave principle. Now with reference, we will keep referring to the chart, okay, as and when required. Now whatever I have said about J and K, and now about the clock, which is this YC, same as this, okay. Instead of drawing another table with 16 entries, I will straight away go and create the ASM chart for this particular flip flop, okay, because ASM chart is going to give me the whole behavior of the system. What is the system here? It is master slave JK flip-flop. Remember that. Good. Now, we know that it goes, the system goes through states. So, I will arbitrarily talk of starting state, some state, okay, call that state A, okay, and it's arbitrary, quite arbitrary. In state A, I'll just say I assume the output generated is H0. Remember, we were always talking about we are always talking about the state box, and we are always recording the output being generated in that box. Okay? In state A, output generated is 0. Good. Now, shall we take a look at the chart again and see what we are talking about here. Now, let's say we are somewhere here. Okay? There is a present state is 0. The output generated is 0. That's what I mean. In the present state 0, the output generated is being H0. That's what we are talking about. Now, when the present state is 0, that is, these are all the various possible things. Okay? Now take a look. If J and K both are 0, the next state is going to be 0. No change. Take the next case when the present state is 0. If you have J as 0, K as 1, what is the next state? Anyway, K is a reset input, so the next state continues to be 0, no change. So, in other words, as long as J is 0, that is, we are talking about these two cases. As long as J is 0, the state of K does not matter. It does not do anything, right? Now, come to this. The present state is 0. Okay? Now, what is the next state for that? It is 1. And for this one, the present state is 0, next state is 1. Now, take a look at the J and K levels for these two present state 0. When J is 1, right, as long as J is 1, that is here and here, irrespective of whether K is 0 or 1, the present state changes to 1. Agreed? So, actually it does not matter what the value of K is. It only depends on J. Now, let us combine this. Let's get back to the ASM chart and combine that information, whatever I have said, and include it as the input condition, right? In this state A, in which 0 is the output, I am assuming H0 is the output which is generated in present state 0, okay, whatever I have given in the chart earlier. So, in this, it only matters what the value of J is. K need not be checked. And now combine that with whatever I have said earlier about the clock. If the clock were 0, nothing, right? So, as long as J is 0 and the clock is also 0, so that is the symbol for and, as long as J is 0 and the clock is 0, okay, it will continue to generate, continue to be in state 0, that is generate output H0, right, because K does not matter what it is, we already seen. It only depends on J, okay. And now, as long as J is 0, Yj and Yc will also be 0. Now, we will also take Yc is 0. Now, when will this AND combination be 0? It means Yj and Yc 0 really means what? Either J or C or both are 0. For any one of them being 0, this will be 0. So, as long as clock is in 0 level, or as long as Yj is 0, or both being 0, so this is the condition. So, for the present state A, in which I have arbitrarily assumed the output generated is H0, which is equivalent to my assuming the present state of the flip-flop being 0, right, okay, as per the chart. As long as Yj is 0, fine, it will remain. Now, when Yj and Yc becomes 1, okay, actually you can see we have not talked about this kind of a combination earlier. This is a logical AND combination of two inputs. This means both Yj and Yc both are 1. So, somewhere along, well, I will explain those who would like to see that. See, suppose this is the 0 level, this is the 1 level. Now, what we are talking about is this. Okay, see here. This is 0 level, this is the 1 level. Now, we just take a specific instant here. Yj, Yc both are 0. So, that corresponds in the ASM chart to this. Now, take this instant. Okay. In this instant, so let me call this as T1, T2. Now, during T1, Yj, Yc both are 0. Now, during T2, Yj is 1, Yc is still 0. Then again, this holds good. Now, take this instant, T3. Now, I am seeing Yj, Yc both 1. Okay. So, for instance, this is the one. Yj and Yc both are 1. Now, when it is, what did we say earlier? When it is 1, the input alone is sensed. The output should not change. Output will change only for the falling edge. So, there is an internal change in the state, but output will have to continuously be generated as H0 itself. That is, there is a state, let us say state change from A, and let us call this as B. There is a state change from A to B, but the output continues to be H0. That is mainly because of what we had said earlier. Now, the input are sensed only in the racing thing, right. So, now Yj input need not be checked. Yc is all that has to be checked next, mainly because as long as Yc is 1, that is, let us come to this, as long as Yc is 1, that is this duration. Okay. Now, we do not know about Yj, we will come to that later and fill in. As long as Yc is 1, this will continue to be in the same state, because the output should change only for when Yc falls to 0. Now, when Yc falls to 0, that is when Yc becomes 0, then we say there is a state change, and now there will be an output change also, mainly because we have said when Yj becomes 1, the present state 0 should become next state 1, right. Let us go back to the chart and take a look, confirm that again. See, present state 0, the next state is 0 in this. Present state is 0, next state 0 is in this case. The present state is 1, the next state is 1 only for j being 1. Similarly, here too, present state is 0, the next state is 1 only for j being 1, and we have considered the case of j being 1, right. Yj right, yj is that particular one. So, that is we had come from this state to this state mainly because yj was 1. So, it should cause a change in the output, but not until the clock falls from 1 to 0. That is why there is a delay. Now, when it's 0, when that is when the clock is 0, good. There is a change in state C, change in the state to C, from B to C, and now the output that is generated is H1, which corresponds, let us see, to the, let's with reference to the chart, let us see, that corresponds to the next state being 1. Just see here, J is 1, okay, the next state is 1. So, J is 1, the next state is 1, okay, correct. So, actually we are constantly from present state 0 to 1. So, all those 0 to 1 transition, see here, here you have, here also you have, right, okay. So, goes to this. That means basically when the clock falls, then at this instant, okay, we are saying at this instant, we have said the output earlier was 0, now it becomes 1. Suppose I have another waveform, okay, for indicating the H0 and H1, it will look somewhat like this, okay. It is that false, that is what it is. That is, until this time H0 was generated, at this instant H0 goes and H1 is generated, that is what it means, okay. Now, pay some attention to this because we are talking about H1, H0, and we are also talking about level 1, level 0. Okay? Basically, it is nothing but complement of the other one. 0 is complement of 1, and so here also you will find the waveforms as complement. Okay, can work it out. Now, let us see. I said during this transition age, the input is sensed. So, internally at this instant itself, there was a change in the state, but the output, as far as the output is concerned, no change. It continued to be generated as H0. Now, we may even say that this duration corresponds to up to this, it corresponds to state A. Up to this, from here to here, it corresponds to state B, that is this, right, that is what it is. Okay. Now, what about Yj? Suppose if it continues and falls, on the other hand, suppose after this instant, okay, that is after this instant, that is when actually the inputs would have been sensed. Suppose it had gone but fallen here. Now, there are two situations. In follow this, Yj continues for some more time, whereas here Yj falls. Now, the change in the input really does not affect. That in fact is the principle of the master slave, okay, component. That is the main thing. So, the inputs are sensed at a particular instant and outputs are generated at a different instant. But of course, the instant is related by the clock, okay, it is not arbitrarily different. So, if whether J had changed as shown here or as shown here, it does not affect the output. Good. Now, continuing. Now, we are in a state, the present state, in which we have Okay, as we see, we are in a state C in which the output 1 is generated. So this corresponds in the chart for the present state being 1. So like we worked out for present state 0, now take a look at it. The present state is 1, the next state is 1. In this, present state is 1, next state is 0. Okay? Now you can just see there is an, in other words, we say there is a transition from present state 1 to next state, which is also 1, which means the state continues really, right? Now 1 to 0 there is a transition. Now you can see k is 1. Because of k being 1, there is a transition from 1 to 0. When k was 1, as in this case, there is no transition. We know that k is reset input, right? Good. Now what about this case? Again 1 to 1. So k is 0. Now compare this particular one with this. Here we have 1 to 1 transition, and here also we have 1 to 1 transition. Now in both k is 0. J is 0 in one case, 1, that is we are talking about this, 1 in the other case. So whether j is 0 or 1, that is irrespective of j, when k becomes when k is 0, okay, 1 to 1, that is it continues. J, it does not depend on j. Now see this 1 to 0 transition, k is 1, j is 0. Now here again 1 to 0 transition. Now in both the case you can see there is 1 to 0 transition here, 1 to 0 transition here. In this 1 to 0 transition you have k is 1. In this 1 to 0 transition also is k is 1. Now in this, okay, for this transition j is 0, whereas for this transition j is 1. That means it does not depend on j. Agreed? So and 1 to 0 transition, that is in a state when we have the output h1, when it has to go to another state in which it has to generate the output 0, it's not going to depend on j, like what we had earlier, similar, okay, that's it's something like what you may call asymmetrical. So now I can sort of complete this ASM chart by adding these conditions saying that yk is the only one that must be sensed, and now for master slave flip-flop, master slave principle, I also add this signal yc, right? As long as it is 0, the present state in which 1 is generated continues. When it becomes 1, that is when k becomes 1, then shall we check the chart again? When k becomes 1, what's happening? When k, that is we are talking about the present state 1. In this present state 1, k is 0. Now in the present state 1, k is 1. So this is one thing. Now we see that 1 to 0 it may transit. Now in this present state 1, k is 0. So output is still 1. Now on the other hand, in this present state 1, there is transition to 0 because k is 1, right? So 1 to 0 transition takes place, again let's see the chart. 1 to 0 transition takes place when k is 1. So when k is 1, the state transition must take place, but as per the master slave thing, only internal change may take place, output should not change. So again similar to the previous one, we have a state change say from C to D, but the output will continue to be 1, H1. Well, as before, check for the state of C, because the input k was sensed in the raising edge. Now the corresponding output change will take place when it falls to 0. So as long as the clock is 1, sorry, as long as the clock is 1, it continues in the same state generating that output. That's what it means. When the clock falls to 0, then we have a state transition from state D to A when the output also changes. Over. Now you can see that ASM chart describes the behavior of the entire machine. Want to take a look at in the present state 0, in the present state in which the output is 0, J when it becomes 1, ultimately it will lead to a state transition so that output generated will be 1. But that depends on the condition of the clock. When the flip-flop is in state so that it generates an output 1, depending on K, when it becomes 1, there will be change in the output to 0. Again, that depends on the clock. So actually combining this chart information, whatever we have, in which only the J and K had been given, plus the clock which I had given you, we have worked out the ASM chart of this master slave flip-flop, right? So everything that you find in this chart you can verify, everything that you find in this table, that is excitation table, okay, you can verify that that particular thing is satisfied when you follow the various paths in the ASM chart. Instantly, when you go from one state to another state, that particular thing is called a path. It's also called a link path, okay? Yeah, link path. For instance, let's work it out. For the present state A, there are two link paths, right? There are two link paths. What are they? For the present state A, you have one link path that is which takes it back to A, another link path which takes the system to state B. In other words, we say for the present state A, there is one state transition that is possible, which is A to A itself. Now that is one link path. The other link path is state transition A to B. So there are two paths here. Right? A to A, this is one possible transition. A to B is another transition. There are two possible transitions in this. Good. And whatever the change, whichever path you follow, it so happens in this, the output doesn't change. That doesn't matter. Okay? So that's because of the master slave principle we had introduced. Now like this, in present state A, now let us describe the behavior of the system. Now, this is an example we took, right? Now I'll completely explain now. In present state A, generate output H0 and look for the inputs Yj and Yc. If Yj and Yc is 0, no state transition. If Yj, Yc were 1, there is a state transition from A to B. So for this present state A, there are two possible next states. In one case it's A, in another case it is B. And output generated in both the cases happen to be H0. Okay, that's as far as the output part of it. So here you have these link paths, which in fact give you, the link paths actually talk about the next state. This is your present state we are talking about, right? That is the present state. This is the present state. From this present state, we are talking about the next state. And as I was telling you yesterday, or the previous lecture, we have a false next state and a true next state. Right? We have arranged it. That there are only two paths. Two. Good. So it so happens that the false next state is A and the true next state is B. Fine. And that is as far as the next state is concerned. As far as the output is concerned, it's nothing much. You can see that in state A, right, or in state B, whatever be that, the output that is generated is H0, right? That's what we had got here. That's what we have written there. Well, there is one other thing, that is the input or the conditions which must be tested, right? That is, given the present state A, the inputs that must be tested are the conditions of Yj and Yc. These are the two inputs. Even though the system has three inputs, in state A, two of the three inputs must be tested. That's what it says. Okay, it doesn't matter, because that's how the behavior of the system is. Good. Now, we have almost got, say, I think I will create one field, one what we may call as a micro instruction word, right? Because that's what it is basically. That is, for a given present state A, then test, okay, check the conditions of Yj and Yc. Now, the next state, I'll just because there are two next states, no? That is, one is a true next state and the other is a false next state. So I have to record that here. So the true next state is this, false next state is this. So the true next state for the present state A, it is B, and the false next state is A, and the output that must be generated in this particular one, it must generate H0. Right? The same thing I can put in a slightly different form. That is, I can say the system has three inputs, Yj, Yc and Yk. Or I'll do it for the present state A. Okay. For the present state A, the system has Yj, Yc and Yk, of which Yj and Yc must be tested in present state A. Yk need not be tested. The next state, the true next state of A is B. I'm just writing the same thing down. And the false next state of the present state is A. And among the outputs that must be generated, we have two, H0 and H1, of which in present state A, H0 must be generated and H1 is not to be generated. Agreed? Now, what did we start with? We started with a flip-flop and started saying it had two states essentially. And then depending on the state in which it is, it generates a 0 or a 1 output. Right? For generating a 0 or a 1, essentially you need your two-state machine, just two states. But what is it that we are having? We are having a 4-state machine. Why is it? Mainly because we have introduced the master slave thing. Because of that we have 4 states. Now here we have a 4 state machine and we have 3 inputs to be checked and 2 outputs to be generated. So with this we will try to see what is a microprogram control and what is the hardwired control, because it is easy for us to discuss and deal with. Good. Now because there are 4 states, I can now implement the memory element in the state machine. Okay, remember what is it we are talking about, the state memory, right? Go back to the and recall the generalized state machine model. We had a state memory, right, which is the one which holds all the states, and here we have 4 states. So that particular memory element must be either in A or B or C or in D. That's what it means. At any time the machine is only in one of the states. So for representing 4 states you need at least 2 memory elements, right, 2 memory cells. That's why so. If I call these memory elements as A and B, then these 2 memory elements can be either in 0 0 or 0 1 or 1 0 or 1 1 states. So there are 4 possibilities. The memory, any specific memory element will be either in 0 or 1. So with 2 memory elements we can represent the whole thing, right. So since this is a 4 state machine, we need 2 memory elements, and I'll have them, instead of calling them A, B and C, D, okay, that's using the lower case. Now I'll be having 2 memory elements and call these as state variables. Okay, these are 2 variables, capital A and capital B, which represent the states of the machine. Now arbitrarily I will assume 0 0 as the code for state A and 0 1 for the state B. I said arbitrary. Okay, 1 1 for state C and 1 0 for state D. So I just arbitrarily assume there are 4 possibilities. So 0 0 0 1 1 1 and 1 0. Okay, though I said arbitrary, there is some reason for this, but I will not go into it at this stage. So now here I can rewrite. I can go back to this. Instead of A, what is it we have? Instead of A, I can write the code 0 0. That is my present state. Instead of A, I am writing 0 0. Instead of B, I will write 0 1. Good. Now here, okay, here we have the entire information for the present state A, the code of which is 0 0, right. So what it says is, in state 0 0, look for inputs yg and yc. That's what this one says. Look for inputs yg and yc, and depending on the input test result being true, the next state is 0 1. If it is false, the next state is 0 0. And in the present state 0 0, generate the output H 0. So this word, okay, this word, the entire thing is giving me information about all the link paths. There are only 2 though. All the link paths for the present state. right? Now extend, go to state B, work out similarly, go to state C, work out similarly, go to state D, work out similarly, and we have talked about the entire system. So with 4 such words, we have the whole behavior of this master slave JK flip-flop system completely defined. And that information, when it is given to the controller, we are actually implementing the flip-flop itself, that is that particular element itself. Agreed? So we will continue further on with this in the next lecture.